up here last session, so we ended up talking about the language models, and we started to play around with the problem of generating text, right? So we wanted to generate a text. It was basically designing a language model, and this was the main problem we started with. So we want to model a neural network which is able to generate a coherent text out of an incomplete text. So it's going to get one incomplete text, and then it's going to generate a complete text, which is coherent. And how did we enter or inject that text into the neural network? How did we do that? How do we represent a text as a mathematical object? Tokenizing first. So we're going to do tokenization, which means that we're going to collect, small units, words, subwords, something like that. We put them in a vocabulary. We put index in front of that. And after that, we're going to do embedding, right? So you're going to get those tokens. You embed them into specific vectors, fixed size vectors. And those vectors are going to help you to represent your text, right? So that was the idea of tokenization. So we ended up writing down a bit more formal version of the language model. So a language model is going to start from a sequence of tokens. Right now, those x's here, x1 to xt, are token indices, right? Token number, for example, 3, which could be one word, right? The, ing, I don't know, am, or. It could be anything, but we're going to represent them with a token index. And then we have this sequence of tokens, x1 to xt. And what we want to do, we want to complete this sequence of tokens, maybe with L extra tokens after that. And we want them to be coherent. And once again, what do we mean by being coherent? Semantic, meaning that the sentence should make sense. And the second thing was syntax. It should just fit the grammatic of the language we're targeting, right? So that was the point where we ended. So we understood that the problem is completing a sequence of tokens. And then the question is how we can formulate this idea of coherency here, right? How we can describe a coherent sequence. So what is a coherent text? What is a coherent text? Well, if you think about it, you would say, OK, something is coherent, something makes sense and is correct, when it's very likely to be said by someone who is native speaker of that language, right? So if there is a native English speaker and they say one specific sentence, that is probably a coherent sentence, right? High probability. So we can, right now, start thinking a bit abstract. And this is the point where I told you you always need to somehow look from the problems in generative models from both perspectives, both computation and statistical. So we're going to look a bit at statistical here. And we're going to try to build upon this intuition that when we say something is coherent, we basically mean that that is very likely to come out of someone who is the speaker. And we can think of that one who is the native speaker of a language to be a kind of ideal language model, right? So if I am a native speaker of one language, probably I'm the best source for that language. So I am actually the language model, ideal one for that language, right? I mean, we can even think of more abstract case, like I am not only native speaker, but I am very highly educated, like the best one you can find. And then I can say very nice sentences, perfectly correct, both from semantic and syntax point of view, right? So this is the way that we can think about a language model in a kind of abstract form. And this totally makes sense because what we say that, OK, if we have one text completion, which is coming out of the mouth of some native speaker, this is with very, very high probability, it's going to be coherent completion. So meaning that it's going to have no mistake in meaning or syntax. And the chance that that person says something totally wrong or grammatically mistaken is very, very low, right? So it might be it's a joke game and they do it, but in general, if you think about it statistically, this is almost impossible that this happens, right? So this is the way that we are going to think about it, and we typically model everything as a kind of probability. distribution. So what we're going to say, okay, say we want to complete a sentence. And the sentence is, it is great to hear that. So now we want to try to see what's going to come after this, right? How we're going to complete it. And now all of us know that if we want to complete this sentence, we have lots of options, right? It is great to hear that. Okay, you have succeeded. Yeah, it makes sense, right? It's great that you have succeeded, grammatically correct. It's great to hear that you have finished it, right? This is still correct, right? This is great to hear that you are happy. Again, this is a correct completion, right? So you have lots of possibilities coming out of it. And each of them probably is happening with some probability. And you don't know what is that probability. That totally makes sense because it's pretty much impossible to find out what is that. But one thing that we can say about this is that if I have this sentence, okay, this is the, say, the chance of this guy turns out to be this number. And don't assume that this is something real. I mean, it's just a dummy number I put here. But the point is that what if I have the next, like this option for completion? It is great to hear that potato is round. Well, it's correct sentence, right? Potato is round. Maybe I am very happy that potato is round. I don't know, right? But the chance of this thing being said is lower than the other one, right? Still, if it's a kind of, fictional story, it might be the case, right? The witch comes out of the house and says, it's great to hear that the potato is round, right? This could happen, but with lower chances compared to the first one, right? What if I think about this one? Potato ate the chicken, right? This is now lower in chance, right? Because it doesn't make sense at all, right? But it's still grammatically correct. And you can keep on thinking of other examples as well, right? Potato am good. So this is now nonsense, right? The sentence is grammatically mistaken. It doesn't have any meaning. And you can keep on going like this. For example, you can give another sentence, right? Kartoffel bin gut. So you start speaking German and then you do grammatical mistake as well, right? So it is pretty much impossible. So you see here, we can think of them going down in the chances, right? In the probabilities. And this that I write down here, 10 to the power minus 15, it means that it's not impossible that it happens. Maybe somebody is just making a kind of fun game, and then they're going to start saying such a sentence. But this simply says that, okay, if you want to complete that one, and you give it to an ideal language model, meaning that you give it to a native English speaker, then out of every 10 to the power 15 people, you're going to hear once somebody says that, right? Now, this makes sense, right? But if you give this sentence, maybe out of every 1,000 people, you find 15 people completing the sentence this way, right? So this is the idea that we call it the language distribution, right? So I hope that you get the idea. This is a kind of a statistical description of what could come next after an incomplete sentence, right? This is what we call a language distribution. So everybody's happy about the idea of language distribution? What I mean? Right? So the language distribution is essentially conditional distribution, which is going to look at the tokens that you have up to one specific time, and then it's going to compute for you the probability of the next tokens coming, right? So if you think about L different tokens after your T tokens that you have seen, so it's going to compute the chances of xt plus 1 to xt plus L, this next L tokens, given the tokens, the T first tokens that you have seen, right? So the first T tokens are the sentence you have incomplete, and the next ones are the ones which you are going to say to complete the sentence, right? And this is a conditional distribution. Definitely there is no deterministic output coming out of this guy, right? So if I give a sentence incomplete to every single of you is going to complete it one way, right? And all of them are correct, but there are definitely some cases none of you is going to use, right? So this is the statistical viewpoint, the language. And now, okay, we got echo here. So now when we talk about a coherent text, we basically mean this is a text being sampled or being drawn from the language distribution. Okay? Again, what does that mean? This means that with very, very high probability, that sentence is going to be correct, both in meaning and in syntax. But there's always a tiny bit of chance that there is a mistake, right? You're talking with a kid and it's just doing a mistake, right? That is still there, right? But they are all chances, meaning that in practice they are not going to happen. Just remember this one. I told you this sentence, for example, say the probability is 10 to the power minus 15. This means that after this sequence, this guy can come out theoretically, right? But the chance is 1 in 10 to the power 15 cases. Now, if you have a random language generator and then you want to run it, how many times you need to run it at least to see once this guy? Probably you need to run it for 10 to the power 15 times. This means that you should push the button for tens or maybe hundreds of centuries, right? Practically, it's not coming out of the language, right? So this is why we say this is, I mean, it's still there. There is a very tiny probability that happening. But when you think about this from a practical point of view, then this is not really happening in practice, right? So there are only a bunch of things that are going to happen in practice. Everybody's happy about the language distribution? So you got the idea? How we describe a language from a statistical point of view? Great. So if you got no question, then let's just complete the definition of the language model, because right now we have the two things we were missing last time. The first thing was how we can represent the text. Okay, now we know this is a sequence of tokens. The second thing is how we want to complete it coherently. It simply means that we want to just give a completion which is sampled from the language distribution, right? Drawn from the language distribution. So this is the definition of the language model in a kind of abstract form. A language model starts from a sequence of tokens, something like this, t different tokens in complete sentence. And then it's going to complete this sequence by giving some extra tokens. And these tokens are sampled from the language distribution. Okay? Everybody's happy? Questions? If you got no question, I have one question. When I say it's sampled from a distribution, what do I mean? How do you sample from a Gaussian distribution? I mean, don't laugh at me. I know this is, but this is an important question. How do you sample a Gaussian distribution? Don't think complicated, just in practice, how you do it. If I tell you, just give me a Gaussian sample, how do you do that? Do you simply write a number? If I write any number in this board, then this means that it's sampled from a Gaussian distribution? No, right? So how you do it in practice, probably you use your computer, right? Yeah? How you do it on your computer? Yeah, go ahead. Yes, regarding the language distribution, you are right. But right now, I'm just talking about the Gaussian distribution, yes?
You just pick randomly, and then that random, we work on the probability of that random distribution later.
Yeah. Again, don't mistake this one. I'm just asking one question general. If I want to just generate one sample drawn from a Gaussian distribution, how can I do it? Computer. You open Python, for instance, right? And then what you do, you're going to sample with the command rand n, right? So yeah, what does that guy do? I told you, this is a very simple question. So what does that guy do? Do you know?
There's a uniform distribution.
It's going to process it into a form that this is a random, this is going to be a Gaussian distribution, right? So if I write down any number on the board, that is not a Gaussian random number, right? So it doesn't mean any number that you say. When I say I'm sampling from a Gaussian distribution, this means that when I do it so many times, then when I put all of those numbers next to each other, you're going to see a Gaussian distribution if I plot the histogram, right? And keep it in mind, this is not always a simple thing to sample from a distribution. For the Gaussian case, that is not that hard. But for other things, it's sometimes quite hard for your computer to generate a random number of that distribution. So if you give any random distribution to your, any arbitrary distribution to your computer, this is not that easy for it to just generate a sample from it. Sometimes it takes time for it to compute because it's going to need to just generate different samples and accept or reject them. Okay? So moral of the story, when I say I am sampling from a distribution, this is really something happening behind the scene. And you don't know it exactly yet, but you're going to gradually start to understand it. Okay? So this is important that you have a bit of feeling about how you sample from a distribution. You can double check it, online. Just go online and check how you can, for example, generate different random numbers. But this is important to remember. It's not like I give you a random distribution and then you're going to immediately sample from it. It's not always the case, okay? But for this particular case, as your friends mentioned, we have something. It's a multinomial distribution, so we can do it. Okay, so now, any questions first? No question? Great. So if you got no question, then let's go ahead and start with a simple language model. So now we know what is the definition. Then let's try to just make it work. Okay, let's try to build one model which is going to complete the sentence. Now what I'm going to do, I'm going to just focus on a single token completion. It means that I want to know just the next word. That's it, right? And then when I can make this, I can gradually make the more complicated ones as well. I can recursively repeat the procedure to generate more tokens. So let's assume I have t different tokens here, and I want to just know the next token, xt plus 1. Or predict it, or generate it, actually. Now, the thing that I need to do, I need to essentially train a model, which means that I need to have the three main components. What are the three main components? The first one is a model, right? I'm going to choose one neural network, one specific architecture, right? The second thing is data set, right? You're going to have a bunch of data samples, which you need to give it to your model and make it understand how it should behave. And the last thing is the training algorithm, right? You're going to define one specific loss, and then you're going to compute that loss on that data set using the model, and then you're going to use some gradient descent-based algorithm to just minimize that loss, right? So this is the general approach for training any deep model, and we're going to stick to that one. Now, for the model, what is the model? Essentially, for us, the model is a neural network, right? So the neural network is going to get whatever I have in my sentence up to this point, so the first t tokens, and it's going to give me as the output something. What is that thing at the output? The next token, yeah, this could be, but is there any better idea, given that we know that we are going to mimic the language distribution? The probability of the next next token, exactly, from the vocabulary, exactly. So the thing that you are going to do is that you're going to give all the tokens that you have up to this point, the t tokens, into your model, and then as the output, you're not just generating one single token, but you generate the probability of every token happening, right? So you're going to say, what is the chance of the next word being the? What is the chance of the next word being bracket? What is the chance of the next word being apple? And so on. Every token that you have inside your vocabulary, you're going to compute the chance of every single of them. Once you have that probability, if that model is trained well, this probability is going to be the language distribution. And you're going to sample from it. You generate one sample which is proportional to that distribution. Okay? So this is the idea. So I'm going to find the chance, the probability of the next word, xt plus 1, being one specific token x, given that I have the first t tokens seen in the sequence, right? So I'm going to compute this one. This is not a single number anymore, right? This is so many numbers. How many numbers do I have here? As much as tokens I have, right? So it's the vocabulary size, exactly, okay? Now, can I do that? Can I make this happening in my model? Do you have any idea from architectures you know? Softmax, great. So I'm going to put one softmax, right? And the softmax is going to have exactly the dimension of my vocabulary size, right? So it's going to give me probabilities exactly as much as tokens I have in my vocabulary. Clear? Okay, great. So let's do it then. Let's say that I have this FW. So this FW is my model. So essentially, this is the neural network. And that neural network has a bunch of parameters in it. So some weights, which are all sorted inside this list W. And then the thing that it's going to do is going to take the first T tokens. And then it's going to generate one probability distribution here. That is the probability of the next token, given the tokens that we have seen, right? So I can think of that probability of the next token, PT plus 1, to be the output of my neural network, which is a one-dimensional vector, and it's a probability vector, right? It means that when I add up everything there, it's going to add up to 1, right? This is what softmax, for instance, does for us, right? Okay, so that is a language model. It's a kind of valid language model. The whole question is that how we can train it, right? So once I have trained it, I can generate the next token, and I can simply do it by sampling from this distribution. So as I mentioned before, sampling from a general distribution is not a simple thing. But for this particular case, where I have a vector of multiple probabilities, this is what we call it multinomial distribution. And you can always sample from it in Python, because there are efficient algorithms that you can implement to sample from this distribution, okay? So for instance, in Python, you usually do PyTorch, you usually do it like this. So you're going to use multinomial comment, and then you give the probability distribution to it, and you just take as much samples as you want, okay? So when I say sampling, again, I don't mean I'm just writing down one random token. If I wanted to do that, I didn't have to just learn anything, right? Just write down random things. It's not the case. I am actually generating proportional to that distribution. This is lots of computation, okay? Questions? Everybody's cool? Great. So now that we have this, now let's make a bit of data that we can train this model on that data. How we can make a data? Basically, we need to make a text corpus, right? So how we can do it, we can just go ahead and find texts that are relevant to what we want to do. For instance, if you look at like practical language models trained, they usually have different corporas, like some of them are text, so like plain English text. Some of them are on programming, so they have a bunch of data which are basically Python programming, I don't know, C programming, MATLAB programming scripts. So they have different forms of corpora, but you could have only a single corpus, right? So you can have just, for instance, one textbook. You just get one textbook, or you get one storybook, and this is your data set. And then one of the popular one is the Wikipedia. So, for example, BERT and many other practical models that nowadays we use, pre-trained and pre-implemented, they are usually trained on Wikipedia. But large models like GPT-4, they are essentially trained on the body of internet. So they call it body of internet. It means that they have curled everything over internet. Then they, of course, filtered it, processed it, and this is a tons of computation and process into making them a kind of a very large, rich corpus of text, which is including anything: programming, text, different languages, anything, right? And then they basically try to train their model on all the data they collected from internet. I mean, of course, there are some safety issues and some cleaning going on, but main body of the internet is there. Okay, now whatever the corpus is, at the end of the day, we can tokenize it, exactly like what we did in the last session, right? So you're going to do the tokenization, you make your vocabulary, and you can write down that text in form of a very, very long sequence of tokens, right? So it's going to be A1, A2, so on till AN, right? A1 is the first token inside your corpus, AN is the last one. And this N is crazy large. BERT is not a big model, and for that one, this is 3.3 billion tokens inside the data set. That is only trained on a part, I'm not sure, not the whole Wikipedia. I think a part of Wikipedia plus some books. That's it, right? So you can imagine how crazy the data set would be for something like GPT, okay? But at the end of the day, it's a huge number of tokens going on there. And then this is the data set that you have, and you need to just train on this one. But if you want to train on the data set, should you compute your loss over the whole data set? Can you do it in one shot? Can I get my model and then try the whole data set and find out what is the loss of this model? No, this is not going to be the case. What do? We essentially do collect data samples from it, right? So you get this huge data set, and then you break it down into few samples. Each sample is a sequence, couple of sentences, for example. And then these data samples are the things that you collect them in the, multiple mini batches, and then you try to go over them in the form of mini batch processing, right? Now, just to give you an idea how you can do it, so that if you want to try it later on, you can simply do it. Let's try to make data samples out of this huge data set. So again, the data set that you see here is a huge text. It means that it can have, as I said here, 3.3 billion tokens in it. But now you want to just take a few samples out of it, maybe 64 samples, because you want to have one batch of 64 to just do one iteration of training, okay? So how we can do it, that is not very hard thing, right? So you're going to randomly choose one index, and this index could be anything between the beginning of your data set towards the end of your data set, right? If you want to make a sequence, a text of length t, then you're going to start from that point j, randomly, and then you're going to take whatever is after this, right? For a sequence of t, right? Then it's going to be one sample for you. So starting from beginning towards the end, this is one sample, right? And then this sample has one label. What is that label? The next word. Great, right? No, the next word right now. Not the probability, the next word, but you can transform that word into the probability by one hot representation, right? So it's again same as the supervised learning here, okay? So what you're going to do, you're going to take your t different samples, and then you're going to go ahead and take the next one to be your label. So you're going to say, okay, if I have this part of the text inside my data set, then the label is the next word, right? The next token. And then you're going to, again, randomly start from one other point inside your corpus, and then you're going to say, okay, I'm going to take a text of length t, then the next word is the label, and so on, right? So you can collect as much as you want from this data set, right? So always randomly sample from this data set as much as you want, and you're going to have, so many samples, right? Everybody's clear? Yeah.
Just one question. So if we sample it randomly, does it mean some tokens get left out?
Yes, that is happening. That is happening. Yeah, but this is not important. I mean, since you are just sampling uniformly, the fraction of those cases are very small as compared to the total data set. So essentially, you are going to go, in each epoch, you are going to go over most of your data set, not all of it necessarily. But you are right. I mean, it might be that I sample here and go, and then I sample again somewhere in between and go, right? And then two samples are overlapping, and this is totally fine. It doesn't change the fact that, the next word is the label, right? So now, usually in practice, you're going to make a batch of, each time that you want to do one iteration of training, you're going to make a batch of data samples. This means that you're going to do this procedure B different times, and every time you're going to collect one sequence, and then you're going to look at the next one as the label, and you put it inside one batch, right? So your batch is going to contain B different examples of incomplete sentences of length T, with the next token being the label. Okay? Everybody's clear? Yep.
Small question.
Yep.
For example, like if you do like sampling, let's say for n rounds,
Yes.
and somehow you encounter cases where T appeared, the same T value appeared like 10 times, let's say. What do you do with these repeated data? Like, do you just put it there, or you just like?
Yeah, this is roughly the same thing as I said. So that could happen with some chances, right? But the chance is very small. Now, if you think about the huge data set that you have, that is very small to happen. Okay? But that happens, and it's not going to harm the fact that, you know, this is still a valid sample, right? Yeah. But this could be the case that, well, you're actually sampling multiple times, and then if you think about the tiny data set and you sample long sequences in it, you sample multiple times, and two of them turn out to be the same thing. Doesn't matter, right? Yeah, I mean, it's compared to the huge number of data that you have, it's not doing anything. But that could very well happen. Yeah.
So basically, we don't do anything about it because we have a huge
Data, yes. Because if you don't want to do that and you want to be very obsessed and just sample very accurately, like not sample, just make accurate fractions, then it's going to make it even harder. So you're not doing this. I mean, in practice, you usually do it that way. But there is always, as you said, there is always ways that you can, you can add more steps here to make sure repetition is not happening, right? You don't do it in practice, though. Yeah. No worries. Questions? So everybody's clear how you make your data set, right? And how you make your batch. Great. So following the question your friends asked, so it's also interesting to think how you define an epoch here, right? Because you're randomly sampling from the whole corpus of data, right? When can you guarantee that you have finished the whole corpus, right? There is actually no exact way. Again, you statistically define it, right? So you said that one epoch is when I roughly have done the whole corpus, right? You cannot define it, but it's good to think about it. I don't want to just complicate stuff right now, but think about it, how you can define epoch in this case, okay? Great. So now that we have the data and we have the model, we just need a training algorithm so that we can train this model, right? So we're going to give every single sample inside the batch to the model. Then we're going to get something out of the model, which is right now a probability distribution. And out of that one, we want to compute a loss, which can help us compute a gradient and push the weights inside our model towards the right values, right? Now, how we can do that, the idea here is to use what we call it maximum likelihood learning or maximum likelihood training. We're going to talk about it once again in the next chapter, okay? But just to give you the rough idea what we do here, what we do essentially here is that we're going to think about this fact that, okay, every single sample that I had in my data, that sequence, the next word was a word coming out of mouth of a native speaker, for example, right? And that is a very likely output that could come, right? Correct? So if my model is really mimicking what the native speaker is doing, then it's going to give high probability to this guy, right? To this next token. And it should not give high probability to other tokens, right? To some other tokens. This is the idea of maximum likelihood. So you're going to play with your model so that you make your model give high probability for the next tokens you have inside your data set. And then you would say, okay, when this happens on this data set, if I have so many data, then gradually this model is going to capture what is really happening inside the language, right? So this is the idea of maximum likelihood training, we're going to talk about it once again next time in the chapter 2 when we just formulate everything concretely. Okay? But right now, we can just write it down based on this, this intuitive idea. So if V is the label of one sequence X, then this V is actually the next token and is coming from a coherent text. This means that this is very likely to happen in practice, right? So this should have very high probability. The thing that we're going to do, we're going to just make our language model to give a probability vector as its output whose corresponding probability for the next token inside the data set is high. Now, how can I write it down? I can write it down in this form. So right now, forget about this L here. Just look at this term. So I am computing the chance of the next word happening being a VB. So this V is essentially the label, the next token inside my data set, right? The label I found from my data set. The chance that the next token is the one I have as the label, given that I have seen already that sample sequence, right? X1 to XD. This chance should be something large, right? This should be something big, because I do know that this label is a likely output. This was inside my data set, right? So I want to do that. So what I want to happen, I want to when I inject this sequence into my model FW, I'm going to see high probability for this label, right? So how can I write it down? Basically, I'm going to give this guy this particular sequence into my model. This is my neural network. So I'm going to inject this guy into my neural network. And then when it goes to the neural network is going to compute one probability, right? One probability vector. And I'm going to look at the probability vector. I'm going to take the entry which corresponds to the token, the next token, the label that I have. Everybody's clear? Questions? So you got what I have computed here, right? So this is what I call it the likelihood of the model, L of W. Likelihood of my model, and my model is only represented by the weights of the model, W. So this is the likelihood that these weights are giving me. Okay? And I want this likelihood to be large. Now in practice, in your batch, you don't have a single sample, right? You have B different samples, correct? So what you're going to do? You think that those samples are independent. Now the chance of all of them happening together is just simply the multiplication of chance of every single one, right? Now if you have a batch, this is the likelihood of your batch. Everybody's clear? Questions? So you got the idea, right? So now the thing that I want to do, I want to maximize this likelihood. So I want this likelihood to be high. And what is the parameter that I can play around with to make this likelihood high? W, your model, right? Your model weights. You want to change the weights of your neural network such that this chance goes up, right? And then you would say, if I do it for so many samples, then this is going to get into a point where this model is mimicking what a true language distribution is doing. Everybody's clear? Great. So what I want to do maximum likelihood. Basically, I want to maximize this likelihood term that I have here. And don't worry, this is not something weird coming from Mars. I mean, basically, this is what you have done before in machine learning courses. Why? Let's do it just simple for once here together, and you're going to see it immediately. So I want to maximize this likelihood. Once again, the likelihood was this guy, right? The product of the output of my neural network for all the samples that I had, right? Now, I want to maximize this guy. If I want to maximize one function, can I maximize its logarithm? Is this the same thing or not? Logarithm is always going up, right? So it's an increasing function. If I maximize the logarithm, it's same as maximizing the function itself, right? So I'm going to maximize the logarithm instead, okay? Everybody's clear? Now, this means that I am going to maximize log of the output of my neural network, right? I'm now looking at the probability itself. I compute the logarithm of that, right? Now, when we are computing this for a batch, this means that we have so many samples, right? they are getting multiplied when I compute the logarithm. What's going to happen? It's going to be summation. Product is going to be summation. So now instead of product, I have a summation. Everybody's cool? Great. So what I am doing, I am maximizing the sum of logarithm of the probabilities coming out of the softmax, the output of my model. And now, instead of maximizing a function, I can minimize its negative, right? That again makes sense, right? Okay, so I can minimize minus logarithm of the output of my neural network. Do you know what is the minus logarithm of the output of neural network at the label point? Have you seen it before in any machine learning course? What is it? Cross entropy. You remember cross entropy definition? So cross entropy, if you compute the probability at the output, right? So you're going to look at that vector. You're going to say, for instance, label is 1. So I'm going to take the first entry. I compute the logarithm minus that. That is your cross entropy, right? So this is basically the cross entropy. And the thing that you are minimizing is essentially the average of your cross entropy over your batch, right? So you basically minimize the average cross entropy over your batch, which is exactly the same thing you used to do in supervised learning, right? So you get your label, and then you compute the cross entropy of this classification problem, and you minimize it. You're doing the same thing here. Now I'm going to call it maximum likelihood, right? But then, I mean, not always maximum likelihood is minimizing cross entropy. For this problem, which is like a classification problem, this is the case. Okay? Everybody's clear? Questions? No question? Yeah? Yes? No, at the point. Here I mean at the point VB. So VB is one of the indices, right? And the output of your neural network is a vector again, right? So the output, this f of w, this guy, f of w, this is one vector, right? And the size of this vector is I, right? So it's going to be p1, p2, and so on till pi. Now, if you have VB, for example, say VB is 2, right? So this means that VB equals by 2. So you're going to look at this guy. Okay? This is the one, right? No worries. Questions? Everybody's clear? Yep. Is index, yes. Is the token index, exactly. It's the index of the next word inside the data set. Right. So in the data set, you have the next token, right? And this is one of your tokens inside the vocabulary. V is its label. Yep.
So can I think of the square bracket VB as the indicator function?
Sorry, which one?
The square bracket VB.
Square bracket, this one? This one? Yeah, this I mean the entry, yes.
Yeah,
the one. Yeah, like indicator. Yes, which takes. Yes. Yes, and then you're going to take it out. Exactly. Questions? No question? Okay. So moral of the story here, at the end of the day, when you are doing maximum likelihood, you are minimizing the cross entropy. And we're going to talk about it once again in the next chapter. There it's going to get more clear. Yeah? So now, you might tell me, okay, it's enough, because enough is enough. I mean, how much you want to always talk about probabilities and a statistical modeling of the language. Can you ever do anything that makes sense? And then, yes, I can do it. And now this is the point where we can do it. So let's start playing around with one simple model and see how it's going to work if you want to train it for sentence completion. So let's start with the basic one, the most basic language model that you can think of, and that is the bigram model. So bigram model, what is it? It's essentially assuming that the whole language is what we call it Markov order 1 process. Now, you don't need to know what is Markov order 1 process right now. The point is that what it assumes is that it doesn't matter what the sentence is, whatever the last token is, this is the guy who is deciding the next token. Okay? So this is the bigram model. Like, you don't look at the whole sentence, you only look at the last word, yeah? And then you're going to predict what is the next word. So if I want to write it down mathematically, it means that the chance of the next token xt plus 1 at any time t, given the whole previous sequence, this is approximately same as the probability of that token given only the previous token. Okay? Everybody's clear? Does it make sense? Is it correct in practice? No, right? I mean, what if the previous token is the, right? THE, right? Then what? What is the next one? It could be any word, right? Any noun. So that doesn't make sense in general. So what we are assuming right now, we assume that the next token is only depending on the current one. This does not make sense. But believe it or not, at some point in time, people used to use this model for completing one single word in a sentence. And it was working, okay? Because it makes sense. Like, if you want to just predict one word in the whole text, and if you do it from both ways, like you go forward in time and backward in time, maybe you do some fine job, right? But in practice, this is something not very useful anymore. But this is good for us because we can start with this one and see how all of this formulation that we have done here work with this one. And based on this one, you pretty much can build anything in future. So all of those, recurrent ones and transformer ones, which we have next, they are going to basically behave the same way. Okay. So everybody happy with bigram? So bigram, quite easy. So last word in the sequence is going to decide for the next token. And now, if we want to just consider one simple bigram, I'm going to consider the most simple bigram ever. So what is the most simple bigram? I assume that every single token that I have is embedded with a vector whose size is exactly my vocabulary size. Okay? Exactly the vocabulary size. If you have 10 words, 10 tokens inside your vocabulary, then the size of every single embedding for them is 10. Okay? And I'm going to pass that vector of size 10 through one softmax. What's going to be at the output of the softmax? It's a probability distribution. What is the dimension of that probability distribution? 10. And this is I'm going to treat it as the probability of the next word. Well, it works in the sense that it's matching what I want. Whether it's going to be a good model or not, that is another question. But right now, it's doing what I want, right? So this is the most simple bigram model you can think of. And if you want to just break it down, you assume that you have I different tokens inside your dictionary. And for every single of them, you're considering one embedding. And every single of those embeddings, these E vectors, they are all I-dimensional. They are all of the same size as the number of rows you have in this vocabulary. Okay? And then you simply just pass this embedding, whatever the word is. If you want to know what is the chance of the next word, you're going to take its embedding, pass it through a softmax. It's going to give you a bunch of probabilities. You're going to sample from that. Okay? Everybody's clear? So say, for instance, I have this sequence. So I have the sequence 6, 4, 3, 1, and I want to know what is the next token. Okay? These numbers that you see here, these are the index of the tokens, right? So this is the 6th token, 4th token, and so on, right? Now, what I'm going to do, I want to find out what is the chances of the next one. So the only guy that is going to play a role in this bigram model is the last token, which is the token by index 1, right? So I'm going to go ahead, I put this E1, which is actually the token of the the embedding of the first token. I pass it through a softmax, and then at the output of the softmax, I am going to have one vector, which is of dimension I, exactly the same dimension of my vocabulary size. Okay? I'm going to take this first one, the chance that the next token is the first token, token index 0. The chance that the next token is the token index 1, and so on till the last one. Everybody's cool? You got the idea? What is the bigram model? Okay, so this is the most simple one that I can think of. And now the question is that how I can use this model. So let's just get back to this model that we had before. Here I am doing a bit of inconsistency, or this is a bit intuitive, because right now here I have 6 different tokens. So what should be the embedding size for every single of them? 6. It cannot be 2-dimensional, right? I'm showing it in 2-dimensional space, but they are not 2-dimensional points. You assume there are 6-dimensional points. Unfortunately, I have not brought my superpowers today to show you 6-dimensional space. I promise I'm going to do it next time. But this is the best I could do today. So now, if I want to just find out, say that I have trained my bigram model. If I want to find out what is the next word, so I'm going to look at the current word. So say whatever the current word is, I'm going to take its embedding. So for instance, the current word is good. So I'm going to take its embedding. I pass it through a softmax. It's going to give me a probability. That probability is of dimension 6. And every single one is giving the chance of the next token, right? Now, if I want to generate the next word, what should I do? Please? What? Not necessarily. Any other idea? Sample from it, right? So not necessarily highest probability, because you don't want to say always the same thing. You're going to sample from it, right? But if it is the right distribution of your language, you're going to give the right word, okay? So we're going to sample from it. So you can think that you have a random generator. You feed the probability into that random generator, and it's going to sample, give you one sample according to that distribution, okay? This is how your model is generating your sample. Now, what if I want to train it? Well, we should just write down the maximum likelihood training that we talked about. Okay, let's do it together. Of course, we want to do it for multiple epochs. That doesn't matter. I mean, we always do that. Now, the first thing that we want to do, we want to make a batch of samples, right? Now, I want to make a batch of samples. How long should be my sample now? How long should be the sample sequence now? One sample, one next label, right? So every single word I assume, the model is assuming that every single token in the text only depends on the previous one, right? So if I want to do that, I'm going to just sample a sequence of length 2. I'm going to take the first one to be my data sample, the next one to be the label, right? So this is, I'm going to do this for b different times so that I have a batch of size b. It means that I look at my whole corpus, and then I just go for randomly take 2 words, 2 words, 2 words, and I collect them as much as I want, right? Now I have made my batch, right? And now I get into the batch loop, so I start just passing every single sample through my model and look at the output, right? So it means that I pass the first, for example, like starting from, for every single of those pairs inside my batch, I'm going to send the first entry, the first token, through my model. I'm going to get one probability distribution at the output. Then I take this probability distribution. I look at the entry which is corresponding to the next token. I look at that probability distribution. I see what is the chance of next token happening, right? And the next token, I do already have it inside my data set, right? So it's the second token here. So I'm going to compute that probability. I compute the logarithm. I compute the gradient of this one, right? And the gradient is being computed with respect to the weights of this model, which is basically only your embedding vectors, right? Now you have one sample gradient. How you can compute, by the way, that sample gradient? How you can compute the gradient here? What is the algorithm that does it? Backpropagation, right? Backpropagation. So we are doing backpropagation here. So the backpropagation is going to compute this gradient for us. We're going to keep doing it for all samples that we have inside our data set, right? Once it's over, then we're going to average those gradients, right? So if we are doing basic stochastic gradient descent, we're going to just average them numerically. If you are doing any other approach, maybe you compute momentum, I don't know, maybe you normalize it, whatever you do, at the end of the day, you average in some way these sample gradients, and then you subtract them with one learning rate from your embedding, right? And you keep on doing it for multiple epochs till this embedding matrix E somehow converges to something meaningful. And then you're going to stop. This is your trained language model. Now if you want to just sample from it, give any word to it, and then get the distribution, sample from that distribution. This is going to be your next word. Everybody's clear? Questions? No questions? OK, so if you got no question, then one thing here, you might tell me that this is like a super basic model, so it doesn't sound like something that works. Well, you're somehow right? So this is going to give you as much as you expect, right? You're not spending so much energy on that, so much computation on that. It's not supposed to do so much for you. But at some point in time, it used to do some basic language modeling tasks. OK? So yeah, I mean, this is maybe capable of just adding one single token to the sentence where the token is missing, if you do a bit of modification there. But at the end of the day, it's not capable of really generating meaningful sentence. And do you have any idea why this is not going to generate a meaningful sentence? What is the issue here? The context is too short, right? So it's only looking at this last token, last word. And in a real language, it doesn't make sense. You can say the next word when you know the whole context before that, right? And you right now have zero memory here. So essentially, the issue with this bigram model is that it has no memory. And this is a very big challenge, right? So it's not going to work. It doesn't matter whatever you do. It's not going to be able to predict properly or generate a coherent text. And the main reason is that every time it's just looking at the last word, right? So it's not about the model complexity itself. It's coming from the fact that a statistical assumption behind the model is wrong, right? Everybody's clear? So any idea how I can extend this one, improve it? Add memory. So instead of the last word, I use the two last words, right? This is going to be 3 gram, right? Not bigram. If you use like n minus 1, it's going to be n gram, right? So this was the idea back when LSTM and after that transformers were not there. So people were thinking about autoregressive modeling of the language. And n gram was a kind of very good model, right? But this is not something that we do anymore. So we can actually do much better than that. And we're going to talk about it after 5 minutes break, OK?